Today I want to explain about star clusters. Let me share my screen. Integrated colors. As for distant galaxies, we are able to observe integrated colors of star clusters. We are able to estimate the age and total metallicity and total mass. And the techniques to have the integrated colors, which we can estimate the age and total mass of that, is aperture photometry for distant star clusters, sum up colors of members for result star clusters. As you see here, this is the ratio of that. And if we have more color, it will be better, that we can integrate more color. And we can have it from starting point are the dereddening colors and absolute magnitudes. For the dereddening, here are the relations from Lato et al. As you see, for the Johnson-Cousins UBVRI system. As you see the correlation here, for the integrated colors, we get these. And most important here is the knowledge of the membership of giants. Here we have color magnitude diagram. Here are giants, and these are important for us, not main sequence for flux. The incompleteness of the lower main sequence is not important because of low absolute magnitude that we have here, low absolute magnitude. So for this diagram, it's not important for us. Mostly giants are important for us. Flux of giants are important in integrated flux or absolute magnitude for flux. We need more giants than these stars in here in the bottom. Here you see we have a zero age main sequence, and we have these stars that they are 25 solar mass, and here stars with 40,000 solar mass. Here you see supergiants, giants, and other stars. And because of luminosity, they shifted in this direction. And for color, giants are not much important. Hot and bright stars or O and B type stars are more important. And giants are old and from low mass stars like Sun. But supergiants are young stars and from high mass stars and are in open clusters. Here you see the relation for 352 galactic open clusters. The age and reddening were taken from the literature, and you see the errors given by Lato et al. And you see the age and integrated dereddening colors. And you see there's a correlation between age and integrated color. Here you see important are the errors for the determination of the uncertainties in log T, and we can have integrated color with age, and we can replace age here and then have the integrated color for each of them, that they are dereddening. As you see, we have 0 here, so it is dereddening. Integrated spectra of star clusters. The idea is clusters of different ages have different stellar contents. Example is old clusters, which their age is more than 100 million years, will not have any very hot O or B type stars and more as members because they have evolved. Technique is slit spectrum over cluster, then integrated spectrum of all members. The assumption is slit covers a representative sample for the cluster. An integrated spectrum of star clusters is how to get a standard library, use isochrones together with initial mass function, let the cluster evolve, calculate an integrated spectrum of what's left in the cluster, taking into account the luminosity of the star. Do this for a wide variety of ages and metallicities. And library for globular clusters is this link. And here you see the work from someone in Argentina that they got some clusters, and then they had the extinction and age of them and compare them to each other, as you see here. Here you see the integrated spectra of age and metallicity. Here we have young clusters, then they goes to the age of the old clusters. So we have old clusters here in the bottom, and we have young clusters here in the top. You see the lines of young clusters and the lines of old clusters. We have more line, emission line, more lines for young cluster and less line for old clusters. And here you see the metallicity. Also for young clusters, we have more metallicity, and but for old clusters, we have less metallicity, as you see here. Here we have the equivalent widths for hydrogen, and we can say that there is no correlation between hydrogen lines and metallicity, as you see. But there is a correlation between hydrogen lines and age, as you see here. Here we have 11 in the right, NGC or NGC 6705, total mass, about 10,000 solar mass, and it has 200 million years old. In the left, you see Orion Nebula, the distance between about 450 parsec, total mass about 5,000 solar mass, and diameter about 3 parsec. And we can say for here for Orion, and we have some local magnetic field, as you see here, and there's a huge magnetic field that this is the field of magnetic in the Orion. Star will be born here. Cluster formation. Observation versus models, and important parameters are time scale, total mass, initial mass function, velocity distribution, binary fraction, diameter, and density distribution. Here we have distribution of young open clusters and star-forming regions. And we have Sun here in 0, 0, and then we have Scorpio, OB2, here, which is near to our sun. And then we have Orion, OB1. After Scorpius, it is near. And then we have some star forming region near it. Here is the same map like this in another way. The stars hotter than BO and BO to B2. You see here, and here is our sun, and this is Scorpio OB2, and this is Orion, and you see different stars in different directions. And these stars is somehow we can say they are from Scorpios, that they left their clusters already, and then they are in the region in all directions. Giant molecular cloud. Star clusters can only form within giant molecular clouds with a high enough initial mass. The stellar formation rate in the solar neighborhood is very low, but still there have to exist several giant molecular clouds to form star clusters. Is the formation process the same for all observed galaxy types? It's a question. And here we can see that the recent investigation of the CO13 gas within 2000 parsecs around the sun, the number of young open clusters can be very well explained, and formation rate of 0.45 open clusters per kiloparsec power -2 over million years in the galactic disk within 2 kiloparsecs around the sun. And you see here that there's a star cluster and single and binaries, and all at far distance and all at near distance. Near our sun, we have less star clusters. Here we have NGC 6611 or M16 with the distance of 1750 parsec, and the age is 8 million years. It has a star formation life. It has the name is gaseous pillars or M16, which Hubble Space Telescope took this picture, and in these clouds a star will be formed. These are the star formation here, that it shows that a star will form in these regions, or they form already, because we see the stars in the past. We cannot detect them now because we should integrate the color and flux. Initial mass function. The initial mass function describes the mass distribution for a population of stars when they are formed together. Relevant astrophysics assigns total mass and metallicity of the initial giant molecular cloud, fragmentation of the giant molecular cloud, and conservation of the angular momentum, local and global magnetic fields, accretion in the pre-main sequence phase. The only observational parameter for the test of stellar formation and evolution models. We observe a luminosity function which has to be transformed to the initial mass function. Initial mass function, there are some questions about that several most important questions are still not solved. For example, is the initial mass function homogeneous within the Milky Way? Is the initial mass function constant throughout time? What is the influence of the local and global magnetic field on the initial mass function? What is the influence of the local and global metallicity on the initial mass function? Thank you for your attention and see you next time. Bye.